All right, guys, so we are now moving on to section 10.3, simplifying radical expressions. So we're going to use the product rule for radicals. So the product rule for radicals is very simple. It's saying that if you have two radicals that have the same root, then we will multiply the insides. So in this case, we have the nth root of a times the nth root of b, which equals the nth root of a times b. Pretty straight. So if we look here, we have the square root of 3 times the square root of 5. So again, the roots are the same. So I check and make sure my roots are the same, and my roots are the same. So that's good to go. So I'm going to convert it into 3 times 5, which makes the square root of 15. If you look at b, on b again, I have perfect matching roots. I have the cube root of 4 and the cube root of 2. My roots are the same. Going to multiply the insides, and I get 4 times 2 is 8, and the cube root of 8 equals 2. If we forget why the cube root of 8 is 2, kind of remember our tree. 8 breaks down to be 4 times 2. There's 1 prime. 4 breaks down to be 2 times 2. There's 2 more primes. So it's the cube root, so I'm looking for the group of 3. And my group of 3 is made up of 2, so the cube root of 8 is 2. Next, we have fractions, some of y'all's least favorite thing, but it's the square root of 2/8 times the square root of b thirds. And so I'm going to put them under the same root, and I just multiply. 2 times b is 2b, 3 times a is 3a. So I hope that's okay with you. Next, we have the quotient rule for radicals, and the quotient rule for radicals is if you have radicals being division underneath the radical, you can separate it. And so it can, instead of having the nth root of a divided by b, it can become the nth root of a divided by the nth root of b. And the reason why you would want this is because sometimes you can simplify either the numerator or the denominator. So in this case, we would have the square root of 5/16. So we can switch it to the square root of 5 over the square root of 16. Square root of 5 doesn't exist, but the square root of 16 does, and it's 4 because 4 times 4 is 16. So our answer would be the square root of 5 over 4. If you look at b, we have the square root of 40 over the square root of 81. Square root of 40 is not perfect, but it can be simplified. So if we have the square root of 40, it breaks down to become 10 times 4, and 10 is made up of 2 primes, so we can leave 10 alone, but 4 is made up of 2 and 2, right? So here is a pair of 2's that can go out, and we're left with the square root of 10. So that leaves us with 10 square root of 10, 2 times square root of 10 over 9. And that's it. Oh, we got it. Oh no. All of my work disappeared. Here we go. I could take out a pair of 2's is where we're at, and I could take out a pair of 5's, and I was left with 3. So 2 times 5 is 10, and the 3 would stay on the inside. So it would simplify to be 10 square root of 3. Square root of 15, well, 15 is only made up of primes, 3 and 5. So therefore, there's no perfect square factor, so the radical is already simplified. All right, now 16. 16, we're talking about, not 16, cube root. Cube root, we're looking for groups of 3's, or thinking of our perfect cube numbers. So if I have 16, a perfect cube is 8. So the cube root of 8 and the cube root of 2 is how we can separate it if you don't want to do your prime tree. Remember, the cube root of 8 is 2, and the cube root of 2 doesn't exist, so it's already simplified. Here we have a quotient, and that means using the quotient rule, we can separate them, and we can have the cube root of 3 over the cube root of 64, we've taken the cube root of 64 a few times now, and so we know that the cube root of 64 is 4. It is a good idea to kind of know your squares and your roots, not your roots, your squares and your cubes, maybe up to 10. It will help you if you kind of practice those and get those together, then it could essentially help you along the way. So, square root of x to the 7. So what do we do with variables? There's a couple ways to look at it. You can, with it, the square, you can basically separate it and think, okay, I have x to the 6 times x. And so x to the 6, and take the square root of x to the 6, which gives you x to the 3rd, and it leaves you the square root of x. So that's one way. The other way to think about it is that you're just dividing, and you want to know what you would have remaining, in a sense. So essentially I'm asking myself, how many times does 2 go into 7? Well, 2 goes into 7 3, and I have 1 remaining x. So that's one way to think about it. And the reason why I say that is because, remember, this is the same thing as saying x. Oh, let me choose a different color. X sorry, my pen and I are not getting along. X, and remember my root here is 2 to the 7/2. So you're asking yourself, what is 7 divided by 2? Well, 7 divided by 2 is x to the 3rd. And so this would become x to the 3rd. And then you're left with 1/2 left over, right? 1 out of 2 left over. So that gives you x to the 3rd, and 1/2 means you're taking the square root of x. So the key thing with square roots is that you're separating. You want to know what's the largest even number, essentially. So I have the square root of 20 over the square root of x to the 16. So 16 square root of 20 is 4 times 5. And so square root of 4 times square root of 5. Square root of 4 is a perfect square. Square root of 5 is not. On your denominator, you have x to the 16 underneath the radical. And 16 divided by 2 is 8. So x to the 8th. And together we get 2 square root of 5 to the 2 to the square root of 2 times the square root of 5 over x to the 8th. Oh, a lot more variables. Whoa. All right, so now we have 3 different monomials. Well, technically you can call them 3 different monomials, I guess. So we can separate them all if we wanted to, or keep it all under one radical. So 54 breaks down to become 27 times 2, x to the 6 times y to the 6 times y squared. The reason why you're looking for 6's, or you use 6, is because you're trying to find multiple exponents that are the multiples of 3. So for example, 6, 9, 12, those are all multiples of 3. And what we're going to do is finish it. So x 2 and y squared, they can't be simplified because there's 2's prime and y squared is not a multiple of 3. The power is not a multiple of 3, so we're just going to move those to the end, notice. And then the rest we're going to actually break down. Well, we've talked about multiple times what the cube root of 27 is, and the cube root of 27 is 3. And 6 divided by 3 is 2, so it becomes 3x squared times y squared times the cube root of 2y squared. So now we have our quotient rules, and we're going to practice using the quotient rule. And so if we have the square root of 20 over the square root of 5, the square root of 20 we've discussed breaks down to become the square root of 4 over 2. Sorry. Oh, I'm sorry. So we can use the quotient rule to go backwards. So if we have 2 radicals being divided, as long as it's the same type of radical, they can become under the one radical. And 20 divided by 5 is 4. And so the square root of 4 is 2. If you chose to keep it as is, you could simplify the square root of 20 over the square root of 5. And we've done this before, and we got the square root of 20. Remember, simplify it to become 4 square root of 5. And you already have a square root of 5. So your square root of 5s would cancel out. I think I did that backwards. I'm so sorry. I didn't mean to write 4. That was the square root of 4. There's my square root. Square root of 4 times square root of 5. And it cancels out the 5. And then the square root of 4 is still going to lead you to 2. So you either can combine the radicals or keep them separate and cancel out. Here we have cube roots. Remember, cube root, you're asking yourself what number times itself 3 times will produce 48. So you're trying to think, like, is there a number? If you said no, good job. So 48, when we look at it, it can become, after we simplify it, so 48 divided by 2 is 24. So now we're down to 24. Let me reverse what I said. So we're going to combine the radicals. So we end up with 7 times the cube root of 48y to the 4th divided by 2y. So we're going to simplify, clean this up. 48 divided by 2 is 24. Y to the 4th divided by y. Remember, there's that invisible 1. That means we're going to subtract. So 4 minus 1 is 3. So this simplifies to 24y cubed. And now I'm asking myself, is there a perfect cube that will multiply by something to give me 24? I'm like, what about 8? 8 does. So I can end up with 8 times 3 is 24, and then I have y to the 3rd. And so I'm going to keep simplifying this. Well, the cube root of 8 is 2. The cube root of y to the 3rd is 1. Is 1y, so therefore I'm going to keep them together because I know that they can be simplified. The cube root of 3 is 3's prime, so it's just stuck. And so I end up with 7 times 2y to the 3rd, and 2y times the cube root of 3. I'm going to keep simplifying, so 7 times 2 makes 14. And so my final answer is 14y times the cube root of 3. Now we're going to talk about the distance and midpoint formulas. By use of the Pythagorean theorem, we can derive the formula to find the distance between 2 points. My favorite things about formulas is that all you're doing is plugging in. You're given 2 points, x1, y1, x2, y2, and you plug them where they go into the formula. So where it says x2, I put that value. Where it says x1, I put that value. So example, I'm given the point -5, 8 and -2, 2. Now I have my formula. I'm going to label what I have. So just numbering from left to right. So here's my x1, y1, x2, y2. Numbered from left to right. I'm going to plug them in where they go. I see that I numbered the other way. My bad. So this is to show you that you can switch your x1s and y1s around, your x1 and x2 around, and your y1 and y2 around. You just have to make sure if you switch one, you switch both. Otherwise, it doesn't work. So here we are. We have -5 minus -2 squared plus 8 minus 2 squared. I'm going to clean it up. -5 minus -2 makes -3. 8 minus 2 makes 6. -3 squared is 9, and 6 squared is 36. And 9 plus 36 is 45. And the square root of 45 equals 3 square root of 5. The reason why is because the square root of 45 is made up of 9 times 5. 9 is a perfect square, so I can take the square root of 9, and that gives me 3, and 5 can stay inside. It's kind of tough right there. So that leaves me with 3 square root of 5. Midpoint formula. Midpoint formula is another lovely thing because you're literally just plugging in the values that are being given to you. And on this example also, as long as you switch x1 and x2 the same way you switch y1 and y2, it does not matter which order you put them in. So got it. So if I have the points -5, 8 and the point -2, 2, here's my formula. I plug in the numbers. So if you notice that -5 and 8 are in the front, -2 and +2 are the second numbers. I'm going to clean it up. So -5 plus -2 is -7, 8 plus 2 is 10, and I can keep simplifying. 10 divided by 2 is 5, and if I want to write it as a decimal, I can write -7.5 is a -3.5, and that is midpoint.